and MLOps. A lot of MLOps seems to be more focused on either computer vision use cases, sometimes like fraud detection use cases. I feel like recommender systems get a little less love on that front, which is unfortunate because a lot of probably the most interesting and valuable use cases of MLOps come to recommender systems. However, recommender systems are quite different. And let's talk about why. So let me share. So I'll start by talking about what I'll call the simplest model. So this is the way we are all taught um, machine learning when we first learn it, which is that we have these features, and typically they come in these, this perfect CSV where each column is a feature. We train some sort of model on top of it, and then it makes predictions over that. So features are just inputs to models in this definition. And this is kind of the traditional first way you learn machine learning. Now, if you've ever done machine learning in production or in a real use case, you'll know that actually those features don't come out perfectly, typically. Oh, someone said they can't see my screen sharing. Marie, can you see it on your side?
Um, I can see it on my end.
Cool.
Yes.
Okay. Yeah, if you can't see it, I'm not sure what to tell you. Maybe try refreshing your.
Oh, yeah, he can see it
Oh,
now.
cool. Awesome. Okay. So, uh, yeah, features are inputs to models. They are, yeah, I mean, the process of feature engineering ends up being a core component of the ML lifecycle. And specifically for recommender systems, it's a huge piece of it. Before I go any further, I probably should, give a bit of an introduction on myself, especially given how relevant it is to today's talk. So my background is actually in um, recommendation systems. I started my career as a software engineer. I started a company that was doing personalization at scale. We were handling about 100 million monthly active users, predicting subscription, predicting churn, and most importantly, doing personalization. So we built a recommender system for that. And so a lot of the MLOps that I've learned and built has actually been around the use case of a recommendation system. Interestingly, it is also the kind of initial reason why Feature Form, the company I started, exists. It was built for recommender systems originally. In my time doing recommendation systems, I found that the most value in building those types of models comes from the feature engineering. So here's what I mean by that. In recommender systems, I was typically given some sort of data source. It could be clicks, maybe transactions people make. I'd have a variety of different data sources. A lot of times they'd be streaming, and I would take them and they would be really raw and kind of not super consistent all the time. And I would transform them into features. So I would come up with these transformations to come up with features. And those features were essentially signals that I could use to make recommendations. Um, those signals could be things like the last item a user listened to. Maybe if you're doing like music recommendations, you can get really interesting and do content-based features such as the beats per minute in the song or the key that it's in. It could be derivative features of if you have a song, you can look at the artist and then you can figure out where the artist is from or what language they speak, and that might be a feature. So all these things would come in, we'd come up with all these different features. We would build them for training. So we would kind of go and build the features as they existed over time. What I mean by that is recommender systems are inherently a time series problem. So when we're making recommendations, and training a system to do it, we actually have to know that people's tastes and what's popular changes dramatically over time. So you can't just train naively. You need time to be a component in a feature, which means that you need to generate your features. Every new feature that I would come up with, I wouldn't just need to be able to generate the values today. I would need to generate the values historically so I could do point in time correct features. And so that's the training store. And then the inference store, I would also need a cache where I would pre-process my features because it's if I'm doing millions of recommendations a day, it's not really possible to query, like user events and build those features every single time they need a recommendation. It would be far too long. The other big problem of recommendation systems is latency is super, super important. So to power all this whole pipeline, I would build it on top of data infrastructure. So I would use things like Spark or S3 or Kafka or Redis or whatever to actually build these data pipelines. And so the majority of my time and my team's time on the recommender system side was actually spent building and iterating on features. So feature engineering almost always drove the most impact, so like the highest ROI, and it also took up the most time. So I'm gonna continue. If I should also add, if you have any questions, feel free to throw them in the Q&A. Marie and I will try to keep an eye on it and respond to them as we can. If you're following along on LinkedIn or on Twitter, you can also leave your comments there and we will try to respond to them promptly. Marie will kind of pull them into here. There are other components that come into feature engineering that are a bit out of scope for, I'll talk a bit about them, but it's kind of the things that people don't think about as much, like monitoring, governance, search and discovery, reuse, versioning. There's a lot of other components to it. But the core is building data pipelines to feed your models for both training and for inference. Now, one specific type of feature that is extremely common in recommender systems, but perhaps much less so in other problems like fraud detection, are embeddings. Embeddings are, I mean, I guess nowadays they've kind of repopularized because of or have become even more popular due to LLMs and RAG. But embeddings actually predate that. And the original uses of embeddings were for NLP, and recommender systems kind of followed then after by pretty much applying NLP-like strategies to user events. So what is an embedding? An embedding is, at its core, it's a vector. And we're going to build some actually in this workshop. But at its core, a user embedding is a vector. It is n number of floats. So it's a list. An embedding has this interesting characteristic where it tries to kind of capture the nuance of what a thing is. So you have like a word embedding, and then it will try to catch the nuance of the word, or a item embedding like we have here, or your user embedding. And so if you do like a user embedding, you will kind of capture some more nuanced parts of the user's likes and characteristics that would have been really hard to capture in more kind of manual traditional feature engineering. So embeddings have this characteristic. They're vectors and they have the characteristics where things that are close together are similar. So things tend to cluster. And therefore, you can use them to do things like recommendations. Because if you have an item, you can use that embedding and you can feed it with other features and other models and get really creative. But one of the simplest types of recommendation systems is just doing a nearest neighbor lookup on an item embedding. So if I want to get items similar to X, then find the n nearest neighbors in embedding space. So the nearest neighbor lookup is really common. And what we're going to do today in our workshop. Now, I should add that there are many other approaches to recommender systems. One that I think it's a lot of what I used to build and the recommender systems I built is better shown on the right here. So on the right, there's a model. This model is actually one of the two models, or one of a few models rather, that powers YouTube's recommendations. And so you'll notice that it's a more traditional deep learning model. It's a deeply connected model with 3 layers or 3 hidden layers. And we're actually feeding in embeddings along with more traditional features into the model to allow it to make a prediction. So rather than if I have a video ID, if I give a video ID, just like the number, the model won't be able to properly abstract between different videos that are similar because it will treat each video as a completely new unique token. Embeddings better capture what the video actually is. So one trick, like it does here, is pass in the video embeddings either as features, or you can even average them together to generate a feature. And then you feed it in as you would any other feature into the model. So one thing that's has become like also again more popular, especially with RAG and LLMs, but again predates both of those concepts, is vector databases. Vector databases allow us to do nearest neighbor quickly because doing a nearest neighbor search is actually a very slow operation if you do it naively because it doesn't scale well. So vector databases actually do approximate nearest neighbor search. So they aren't perfect, but they are much faster. And for things like recommender systems, you don't actually need it to be perfect. You just want it to be really good. So in this example today, we're going to be using Pinecone as our vector database, but you can use one of many. There's Weaviate, there's Quadrant, there's lots of them. Embeddings are created. So how do we create embeddings? Like how do we get these magic vectors that properly capture the nuance of like a user or an item or a paragraph or something? So this slide probably self-explanatory, I'm sure. The way we do it is using models called transformers, which is not to be confused with the talking robots. Transformers are better shown with this model on the left, which is a example of a transformer. Actually, GPT itself is a transformer. There's technically there used to be less of a difference, but nowadays there's kind of a big difference between like decoder only models and encoder only models. So encoder models are ones that take something like text and turn it into an embedding. Decoder models, on the other hand, can go from like text to text, as we see with GPT. One of the first really popular transformer model, which predates GPT and predates a lot of these things, but actually is a kind of technical foundation of them, is a model called BERT, like the yellow dude on the right here. And so a lot of what came to be around transformers actually starts with a model called BERT, which was specifically meant to take text and turn it into an embedding. Okay. So with feature engineering, like I said, you can build all these different types of features. You use those features as signals. So you can get things like a user's favorite song and top 5 things the user clicked on, all sorts of different features. We feed those into a model, and those models make predictions. One special type of feature is an embedding, which is a vector that allows you to do nearest neighbor search or just feed it directly as a normal feature to also kind of feed into that model pipeline. So how about MLOps? Where does MLOps fit into this whole thing? So one core piece of infrastructure that we built for our recommender system, which is a feature store. And when people first hear feature stores, just the name implies like, oh, it's a database where features are stored. For some feature stores, this is correct. Like if you look at Databricks' feature store, AWS's feature store, it's just kind of a place that you would store your features. So you would build your feature pipelines, you'd come up with interesting features, you'd kind of dump them into the literal feature store. Now, our approach and our thinking is very different. What we've found with feature form, part of why feature form exists, is we believe that the features are the definitions. They are the logic that builds them. It's not so much that the features are like this table that you output, but rather that features are the actual transformation code itself. And then we would run that to generate the feature data. So the feature is the code, and then the feature data is the thing that gets generated. So we create that distinction. And so what feature form provides then is a framework that makes it really easy to iterate and build new features, which again, a lot of the recommendation systems is just iterating on features, trying new things out. It makes it easy to get things in production. It adds monitoring and other problems or other things that you would need. We kind of do automatically. So all that kind of comes together into the feature form framework. A bit more about it. It has a resource repository, so it will store and version all of your features and transformations. It allows for collaboration via search and discovery, gives you lineage, gives you sharing, tags, groups, projects. It has governance, so plugs right into your governance tools to allow for access control, SSO stuff, audit logs, all that, monitoring and alerting, as well as orchestration. So it's actually running all this data transformations for you so that when you first come up your features in your notebook, it's trivial to get them into production. The 5 value props of a feature store is as follows. They facilitate deployment, enhance collaboration, organize experimentation, increase reliability, and preserve compliance. So when we build a feature, when we're coming up with a feature, like I'm going to do today in my notebook, a lot of what we start with is just kind of taking a data set and just messing around with it, turning it maybe into like a pandas data frame or Spark data frame and just kind of doing stuff to it until we come up with the types of tables that we need. The problem that I used to run into, a lot of teams run into before using a feature store in something like feature form, is that they would have these features finally working in their notebook. They found a way to get the features to maybe even train a model that works on those features. But deploying them into production is pretty much impossible. The reason for that is because in experimentation, you are typically working with a static data set. You can kind of download that data set or some sample of it locally and do whatever you need there. In production, the data is no longer static. The other thing in production is that requests can come at any time. Like someone can use, like you need them all constantly running, which means you need to be able to generate the features at any point in time. And you need this to be resilient. You need this to be monitored. You need all kinds of other stuff around it. So there are 3 types of production features. There are streaming features, batch features, and on-demand features. Streaming and batch features are what I would call pre-processed features. And the most common ones that you'll see in recommender systems, they're features where we're actually constantly building the values of the features for each user. The reason we would do that is for latency purposes. It means that when we serve the recommendations, even if the data is a little bit stale, a little bit older, it's fine because at least the recommendations are done very quickly. Streaming features work directly on streams, which means that the feature values in the inference store will be quite up to date. However, they are more complicated because they are constantly running. So there's kind of more logic and things that you need to do to handle streaming features. Batch features look more like traditional features that you would build, except they tend to run on a schedule or some sort of trigger to run them. And then there's on-demand features. On-demand features are features that where the feature is actually generated at the time of their request. So a user maybe sends let's say you want to build a model which is spam detection, and you want to see if a user's comment is spam. You might featureize that comment, but you can only featureize that comment at the time of the prediction. So you would need to do it as an on-demand feature. We see a lot of different approaches that people take to get their features into production. With some companies, the data scientists do it themselves. They write their own Airflow, PySpark, all the stuff they need to get their stuff in production. The other thing that we see is data scientists hand off their messy notebooks to some like data eng team or some other team that then has to essentially transcompile them to be usable in production, which ends up, one, being very error prone, and two, being very wasteful. The other value props of feature stores and feature form is enhancing collaboration and organizing experimentation. I'm sure we can all kind of resonate with these sorts of problems of just lacking documentation, or things where we have untitled notebooks, we have variables like df final, we have feature table v7, we have all these like shell scripts that we're running, and no feature documentation anywhere. Another value prop of feature stores is increasing reliability. So when features are in production, their values are changing. And if their values change too much, or kind of in a place where the model starts generalizing well, then you can end up with pretty much your models failing in production. And so monitoring and drift monitoring specifically allows you to catch that stuff before it becomes an issue. Awesome. Any questions so far? I'm going to jump into a notebook, and I'm going to walk you through building a recommendation system with feature form now. Cool. If you have questions, as always, throw them in the Q&A. Okay. So I have feature form running here. I have some so I have feature form running. I have some providers running. So this is just an internal sandbox. There's all kinds of stuff in it, but really the ones that are important is I'm going to be using Spark, Redis, and Pinecone, and S3 all together to build my feature pipelines for my recommendations. So one thing about feature form is we call a virtual feature store. So it has these things called providers that plug into it, and it will essentially orchestrate those providers to build your features for you. There are two types. There are offline stores and inference stores. Offline stores are kind of where the heavy work happens. It's where the storage and the compute happens. And then there's the inference store, which is just where the low latency serving happens. Okay. So the first thing we're going to do, we'll import feature form. We'll create a client and point it at the sandbox that we're using for this demo. We'll retrieve our providers. So in this case, I'm retrieving Spark-demo. So like, again, if I was to go here, I should be able to find Spark-demo. I have like 30, 40 of them, but one of these would be Spark-demo. And so I'm grabbing that directly, and it's already configured for me so that I don't even have to I don't have to do much. Like, it's already kind of set up for me so that I can just start using it, which is nice. So when your MLOps teams puts up feature form. They'll set up all your providers for you. Cool. Next thing we're going to do is set up our data sets. There are two types of data sets. There are primary data sets, which is kind of like the raw data, and then there is transformations, which generate other data sets. So one thing that we register here is something called movie metadata. We give a description, we give the file path. And when we apply it, it creates it. Now, in this situation, it already existed. So one thing that feature form does, which is really valuable, is if something already exists, it will actually just use what's already there. So we register all the files. We have movie metadata. We have another one called link small that we set up. And once we set these up, we can start registering transformations on them. So here's a really simple one. We're just casting one of the columns, which isn't an int in the data set, into an int. So to do that, we have, the inputs, which is link small. Link small we registered here. So we're kind of building this like kind of almost like a DAG. We put a function. Someone asked for the IPy notebook. I'll make sure to send the IPy notebook afterwards in the follow-up email, which we'll talk about, so you can play around with it as well. And you can always obviously, feature form is open source, so you can kind of play around with a lot of this stuff yourself. But yeah, here we do a filter. We grab the things that are not null, and then we grab the ones that are null. We make them ints. We apply this. This creates a new thing called cast in. We have another transformation where we're taking two inputs, and then we're joining them together. And we apply this, like joins link metadata. So you can see that a lot of this stuff is pretty straightforward. Like we're just kind of going through and doing our transformations, cleaning up our data sets. Everything we build can be used by other people, which also is valuable. And the other really cool thing is everything in feature form, all of these resources that we built can immediately be converted into a data frame as follows. So here I just did client.dataframe. I called it on one of the feature form resources, and then I got the data frame. Here, I actually start building my embeddings. So I'm gonna get back to this, but I want to first take a moment and show you the dashboard. So all those data sets we built and others all exist in our datasets tab. So you can see all the data sets that exist. So some of these are just like random tests, but we can look at something like vectorized tests. Or even if we go back, we can even go to like, I saw cast to int show up. So if we look at cast to int, well, it doesn't always show up in the same order. So let's do cast to int. Maybe it's not showing up. If we look at a data set, any data set we look at, like for example, if we look at average user transaction DF, this is like in a different demo. But anything I can find, I can actually see how it was defined. I can see the actual logic that was written. I can see who wrote it. I can see its status. This is running. I think someone's doing something on it. I can preview the data. It's running, so I can't preview anything. I can see all this stuff here. I can see any features that depend on it, any labels that depend on it. I can look at other features. I can look at training sets. I can see the lineage. I can even see my models. So the models are just strings. But I can, if I had any models set up, I could actually see the model lineage all the way down to the data set. So I can completely understand my data pipeline all the way through. Okay. Let's get to back to here. So here's my approach. To do these recommendations, all I'm doing is I'm building for every single movie. I'm taking its description and I'm turning that description into an embedding. In this case, I'm just using TF-IDF, which is more or less just counting words to generate a vector. I could get more complicated. We have more complicated examples where we use something like BERT, or there's like a lot of Hugging Face models that we can use that also work better to take a description or any text and turn it into an embedding. So yeah, so here what I do is I take the description, I tokenize it, I remove stop words. Stop words are words that are kind of not useful, like and the. I use TF-IDF, which is a mix of kind of counting how rare words are and then how often they appear in the description. And then I convert this whole thing to a vector. And then I return the columns that I want. So this whole thing comes together, and I end up with the movie ID, the title, and then the features. And the features are nice because they're I can see all the vectors of every single one of them. Now, I can build my training set. If I don't want to use Pinecone to like build my training set, I can actually use Spark as well. And here's another kind of fun example where I actually do a nearest neighbor lookup in Spark. So I'm essentially joining the data frame to itself and then finding the closest neighbor. So this ends up with a final nearest neighbor thing, which is actually the nearest neighbors of every single movie. So in a way, this is almost like the default recommendations, the most similar movies to every single movie in my database. Now you can imagine how much work I can do iterating on this, even building this, like the iterations I would do. All that stuff is kept in feature form. It's all searchable. All that lineage is there. I can see everything I've ever done in feature form, which is really nice and valuable. And yeah, the other thing we can do, which we'll also do, is I can also register an online store or an inference store. So we support like key value lookups, and we also support nearest neighbor lookups. In this case, I'm registering Pinecone. So I have Pinecone is in feature form. Now I can generate my entity. So an entity is something that you associate features to. So I want to create a movie, and I want there's features, excuse me, associated to that movie, but I need. So here's where I generate them. I have an embedding. I have and two features. Once these are applied, one, they're visible in the UI, and two, these take a minute to apply, which is why I'm not running them for you. But you can see here I'm specifying the vector database as Pinecone. And in doing so, I'm putting this embedding in Pinecone. So feature form builds this whole embedding out and then actually copies it into Pinecone for you. For a lookup, if we wanted to do some sort of lookup, we could do something like, well, I guess what I'm really trying to show in this example is more that there are other models that are usable. So here's an example where given a title or any title, I can grab, or any description, I can actually grab this, encode it using another model. So in this case, I'm using sentence transformers. And then I can actually grab an embedding, grab nearest neighbors. Now, I want to be clear, when you build your embeddings, you have to use the same embeddings to end up in the same embedding space. You have to use the same model on both sides. So in this case, it wouldn't work because I'm using a different model on one end, but I'm just leaving this for you as an example of using Hugging Face to do something. So that's right. How are we going to get recommendations? So we can call client.features on our features, in this case, this movie nearest neighbor. We have just a quick trick to grab some of the things I want so I can print something more interesting. And then if there's a match, so if there is a movie that we consider similar, then we print it. And so when I ran earlier get recommendations, client to the movie Casino, it gave me Leaving Las Vegas as a similar movie. And so the way it did this was really simple. All it did was it took the description of casino, took the description of leaving Las Vegas, and then it embedded them both, and then it found that those two things were very similar. And that's how it decided to make that recommendation. Everything I've shown here is a content-based recommendation. So I'm making recommendations based on like content, like descriptions. You could, and it's actually much more common to do them on user behavior. So then you can create user features and features on user behavior. You can actually mix and match them, like user features, item features, and put them together. But yeah, this all kind of comes together to build our model. So in the end, we built providers, we built data sets, we built features. And in this case, we didn't actually train the model because we were just using nearest neighbor. When you're using nearest neighbor, you're kind of just, you don't have to train the model. You're essentially using a pre-trained model to generate embeddings. But we also support more traditional use cases where you'd use labels and build training sets. So the framework's really simple. Feature form is just a way when you're writing your features, you just kind of annotate them with feature form. You give it some metadata. We'll run all that stuff for you. We'll version it. We'll store it. We'll update it. We'll make it searchable. We'll monitor it. We'll do all that stuff for you. You just write your logic as you would without feature form, and it all runs on the same infrastructure you would use anyway. You can register transformations like I showed, features and labels. Everything's versioned. So you can even set versions. And if you don't set a version, we will actually just generate our own version. We have navigation views. We have search and discovery. Scheduling, which I didn't really get into here because the schedule won't run again, but you can specify triggers and those triggers will run. Test runs. So you can see runs that have happened, if they failed, if they've succeeded, if they're running. You can see how all your runs are working. So someone has a good question. So feature form is kind of like Git for ML, and the results are generated. So that allows me to compare changes. Where does feature form store all this data? So the metadata itself is stored within feature form. But like we showed in this example, we use the providers. So like when I'm in the example I did, I used Spark and Pinecone and S3. So when I registered those three, feature form actually runs the transformations on my Spark cluster. It stores the data on the S3 cluster I've attached to, or S3 bucket I've attached to it. And so that's the way it works. So you can think of it like it kind of has the Git element with the orchestration, but it also actually runs these things for you. So there's the orchestration bit too, as well as monitoring. So the versioning and all that is kind of one piece. The thing like I'm showing in this UI, the task runs is another bit where we show your jobs, we show your tasks and all that stuff working. Yeah, and then you can get visibility into all those things as well. So if you have Spark or Postgres or Snowflake running, you can see what's on it, how it's behaving, what jobs we've run on it, etc. Cool. Any questions? Any other questions I can answer for anyone? Yeah. So there's a question of does it have Calibra type capability as well? It does. It actually would fit in with something like Calibra. So we don't really, even though you can do it in feature form, like we have the users, roles, groups, and you can specify that stuff. We don't actually, most of the time what people do is they will create that logic and those rules elsewhere. And then what we do is enforce them for features. So we kind of read and write to Calibra. So it's more of an extension of Calibra and not a replacement of it. But we do have governance and access control as a key component of feature form. That's actually only in enterprise. So two things in enterprise feature form I should add. One is the governance and access control. Another thing is the stream processing. So both those things are not in open source. Awesome. And slide-wise, that's all I have for you today. So if you have more questions, I have some time to answer them. I'm happy to. We have a Slack community, which is a great way to keep up with things, to learn more about feature form, what we're up to. Marie, you want to add any more about what happens now?
Yeah, so thank you guys so much for attending the webinar. I know we had to reschedule, so thank you for still being able to join us. And so after this, I'll send an email with a link to the Slack community, so you guys can join that, ask more questions. And Simba, it does look like we have another question. Oh, what's the Slack URL? I will send that to you guys after this webinar, along with the recording of this webinar. And you're also welcome to reach out to us if you have any more questions. Yes, the code will be shared to you guys. So yeah, I'll send that URL after this webinar.
Awesome.
Yeah, any more questions?
Cool.
All right. Thank you guys so much again, and stay tuned for our next webinar.